The method of cylindrical shells is a second method that we can use to determine the volume of solids that are generated by revolving regions about different axes. It's different from the disc and washer method because we essentially are revolving those rectangles that we had about an axis that's perpendicular to the one that we did before. So let me explain what I mean by that. Suppose I have one of these little rectangles that we've been using to represent our regions that we are revolving. So we're going to revolve this particular rectangle. Now, before we would revolve it about the x-axis or an axis that was parallel to the x-axis. And when we did so, we would end up with something of a disc. So it would look something like this. So when I revolved it, we would get its mirror image on the other side. And then when we revolved it, it would turn into a little disc like so. If there was some space between the axis of revolution and the rectangle, we would end up with what we called a washer, which has that little hole in the middle. It looks like a donut. Donut. Okay? So that's what we did before. The important thing to consider there is that we are revolving about an axis that's kind of, in a sense, if you think of this rectangle as infinitely thin in the x direction, we're doing it around an axis that's perpendicular to that sort of line segment-ish kind of thing. What we're going to do now is we're going to revolve this rectangle not about the x-axis, but about the y-axis. So we've got to get a sense as to the distance here between the y-axis and that. So there, I'm doing that just to help myself measure the distance. Okay, so there's the distance between those two. Over here will be that rectangle that we just drew, its mirror image, that is. And so my goal is to imagine lifting up this rectangle and revolving it about the y-axis to generate something. So it's going to look something like this. Okay, so that's sort of the inside part of that. And here comes the outside part. And this is what it's going to look like. So on the inside, there would be a little shell as well. Okay, and so again, we generate something that's called that looks cylindrical, but this time it's got a gigantic hole in the middle, and that gigantic hole is there because of the distance between the rectangle and the axis of revolution. So in a sense, those holes are built in. There isn't an analogous thing to the washer method when it comes to the cylindrical shell method. So the question then becomes, how do we find the volume? Because what we'll do is we would add another one of these rectangles next to it. I'm doing this one in red. And then we would revolve it about the y-axis, and we would build these up. And the building up thing that I'm discussing is really talking about integration. We would integrate this. So we just need to know what the volume is of one of these little shells. Okay, well, here's how we're going to imagine doing this. I imagine taking this shell and slicing it. I don't have an image of scissors, but we're going to slice it like so. And then we're going to open it up and lay it flat. Okay, so this is what we would end up with. If we do that, we're going to end up with this long box. Okay, it's not a perfect box. There's probably a little bit of a bevel to the edges there, but that's okay. But we end up with this long box. And when we end up with a long box, we want to find its volume. We need to know the length, width, and height. Okay, so this little rectangle right here on the side is kind of like, now I didn't slice it there, but it's kind of like that rectangle there. So if we know two of those dimensions, we'll know two of the dimensions of the shell here. One of those dimensions is this distance back and forth, which is dx, a small change in x. Again, I'm kind of cheating by doing that, but it works out in the end. The other one is however tall the function is. If you want to call this a point on top of this, x comma y. We're moving up and down, so it's the y value, but this is our function y equals f of x. So this distance is f of x. The question is then, what is this distance? Pause for a moment and see if you can take from the picture exactly what that distance is going to be. Okay, did you figure out what that distance is? That distance is really kind of this green distance, not quite perfectly drawn here, but it's the green distance. It's the distance around the shell. Now, yes, it's different here on the inside than it is on the outside, but we're imagining these shells being so thin that that distance is pretty much uniform. Well, the distance around a circle is what's known as the circumference. So this is the circumference. Now, this is where we're going to have to do a little bit of thinking, but the circumference is 2 pi multiplied by the radius. Oh, well, what's the radius of my sphere, or of my cylinder here? Well, we have one more thing to do here to draw the radius. I've actually got it already drawn down here. This is my radius. Now, think about how that distance is measured. It's measured left and right. So it's a distance that's going to be in terms of x if we're measuring left and right. That's a key thing to do in all these kinds of volume problems. Which direction am I measuring? Left and right or up and down? Left and right goes with x, up and down goes with y. And so if you think about this xy pair that I've drawn up here, what I've just done is I've gone from x equals 0 out to the x value there, and so that distance turns out to be exactly x. It will vary if we change the axis of revolution. Maybe I'm not going about the y-axis, which is x equal to 0. Maybe I'm revolving about x equals -2 or something like that. That may change, but in this case it's going to be 2 pi times x. That would be my circumference. When we multiply these three quantities together, we end up with the volume of just the shell. It would be 2 pi times x, f of x dx. Those are our three dimensions. And then to add them all up, here is the generic formula for the volumes by cylindrical shells. Integral from a to b, if we start at a and end at b, 2 pi times x, f of x dx. And I like to, just as most people do, pull the 2 pi out front as we're doing these calculations. So this is the generic formula. We'll manipulate it when we need to make some different changes here. Here again are some problem-solving strategies. Again, you have to draw the picture. You have to draw the graphs to know what region we're talking about. Draw a typical rectangle, and if you need to, draw more rectangles so that you know the top and the bottom of those shells, or the rectangles. Label the radius of the shells. You got to draw it. Okay, the better the picture you draw, the more likely you are to get the right answer. And then again, use the idea that the volume of the shell is the thickness of the shell, which in our case we called it dx, multiplied by the area of the flattened shell. Well, the area of the flattened shell would be the circumference multiplied by the height. Okay. I like to think of these shells as if you could take a soup can with a weak glue on the label and just kind of twist the little glue off, and then you can just pull the soup can label off. It's kind of like a soup can label, but even thinner than the paper of the label. So here we have an example here where we've got the region bounded by the x-axis, sine of x from 0 to pi. We're going to revolve about the y-axis. In my previous video, we did one of these where we revolved it about the x-axis. So here is our shaky graph. That's one of the worst sine functions I've ever drawn, but it's the right idea. Don't give me too much grief about it. And so here is the region that we are revolving about the y-axis this time. In general, you don't necessarily have to know which method you're dealing with. I know that I've been given y as a function of x. Okay? And so, since I've been given y as a function of x, I would think about having rectangles, and I had to draw one that was so far away from the x-axis there, didn't I? I think about taking one of these rectangles that's thin in the x direction, thickness of dx. If I pick it up and revolve it about the y-axis, what kind of object am I going to generate? Well, I draw the mirror image way over here, and I'm suddenly starting to feel that I'm getting a cylindrical shell. Yes, I am. Okay. I often like to start with whatever variable I am given a function of. So what do I mean by that? Here I'm given y as a function of x, and so I start to think, well, what if it's the thickness dx, since I just covered that other one up? What method would I use? Let's think about the shell once again. When we lay it all out, it's going to have the shape of a box. I'm going to draw the little box down here. Okay, that distance there is that little piece dx. The height of the box, I haven't drawn my box yet, but the height of the box is the y value of an ordered pair, and the y value of an ordered pair is the sine of x. So going this way, we've got the sine of x, and then I'm going to have that long shell like so, and remember that this is the circumference. Well, the circumference, once again, is 2 pi times the radius. The radius is the distance from the axis. In our case, the axis is the y-axis, the axis of revolution. The distance from the axis out to the rectangle. Okay, so that's the distance. We're starting at 0 and moving out to x, so the radius is going to be equal to x. So our circumference is going to be 2 pi times x. And then we take all of these quantities, 2 pi times x, we take dx, and we take the sine of x, and we put them together. And so my volume is going to be 2 pi times x. Well, I'm going to pull the 2 pi out front. We're going to go, we haven't discussed this, but the starting value for my x value is 0, and we make our way out to pi. So we're going to go from 0 to pi. And then we're going to have x times the sine of x dx. Now, where did that stuff come from? The x came from my radius, so 2 pi times x, that's the circumference. Sine of x is the height of the rectangle, and dx is the width of that little shell that we had there. So now we're going to have to evaluate this. I recognize that because the x is in front of the sine of x, I can't evaluate the integral, but if it were gone, I could, which leads me to believe it's an integration by parts problem. So u will be x, dv will be the sine of x dx, du is dx, and v is negative cosine of x dx. So we end up with 2 pi. I'm not going to have a lot of room here, but x times negative cosine of x dx will be negative x cosine of x dx. We subtract v times du. Well, v is a negative, so we're really going to be adding the cosine of x dx there. And I lost my limits. We go from 0 to pi. 0 to pi. The antiderivative of the cosine of x, the sloppy one even, is the sine of x. So we'll go ahead and evaluate that, and then evaluate our expressions at 0 and pi. After we've done this, we end up with 2 pi times negative pi cosine of pi. Cosine of pi is negative 1. 0 times cosine of 0 is 0. We evaluate sine of x at pi and at 0, both of which happen to equal 0. And so our final answer is just 2 pi times negative 1. So our final answer is 2 pi squared. Now, someone usually asks when I teach this, can you do this using the disk and washer method? Yes, you could. Here's the issue, though. If you're going to use the disk and washer method, you're going to have to come up with a formula for x as a function of y. It's given to you where y is a function of x. But you've got to flip that around. If you flip that around, that means you're going to have to use the inverse sine function. And I've never really explored it, but I think if you get to that point, you're going to end up with an integral that's either really ugly or not even one where we have a nice antiderivative. So sometimes shells is absolutely necessary or much preferred. For our next one, what in the world? Sine of x squared. I've never seen such a function. We're going to revolve the region bounded by sine of x squared in the x-axis. They bound a region in the first quadrant that includes the origin. Okay, there are lots of regions in the first quadrant, so we want the region that includes the origin. This region we revolve about the y-axis. We want to find the volume of that solid. This is what the region looks like. Now, if you were to graph it more, it would have something along the lines of, it would go up like, oh, that's not that one. It would go up like so, and then it comes down, and then it comes back up, and then it wiggles. It goes back and forth really fast, so it starts to compress. We're only going to take sort of this first little region in here. We're going to take that region and revolve it about the y-axis. Again, the x-axis would be slightly different and I think probably impossible to do with an integration. But so we'll take one of these rectangles. It was given to me where y is a function of x. So I think rectangles that are thin in the x direction, we'll call them thickness dx. So here we have a rectangle. And we're going to look at its mirror image over the y-axis. So somewhere out here, and when I revolve those, when I connect them, we'll end up with one of these cylindrical shells again. Okay, we'd have a little opening in the back there. All right, so when we slice it open, we'll see that rectangle. So we want to find the dimensions of that rectangle. It is a small change in x as we move left to right. As we move up and down, it is a y value. Our y value is the sine of x squared. And then remember, we splay it out. It looks something like this. And so we need to know this particular distance. This is the circumference, 2 pi times my radius. I think with the shells, it really helps wherever the rectangle intersects, just label the ordered pair x comma y. And so we end up with this distance as my radius. There's the center of my shell. So that's going to be the radius. And that is moving left and right. So that's the x value. We start at 0 and we end at x. So it's 2 pi times x. We'll set all this up. Again, we have to find all of our dimensions. There should be 3 because we have a box. One of them is 2 pi times x, another is dx, and the third is the sine of x squared. Okay, so we put those together to get the volume. Our volume is 2 pi times the integral. Oh, we've got something more to do, but we'll put it all together. 2 pi times x, 2 pi times the radius, times the height of the box, which was f of x. I forgot to write that, but f of x then becomes the sine of x. Not the sine of x, but the sine of x squared. And then the thickness of the box is dx. Now, I can pretty clearly see that we're going to start at x equals 0. But I'm not exactly sure where we'll end. Okay, so where is this second end point? In order to do that, we need to think about the sine function. The ordinary sine function, I'll draw in a small little piece up here, goes something like this. It goes up and it comes down. It reaches its peak at pi over 2. So the next time it hits the ground is at pi. So I know that the sine of pi equals 0. Well, I have the sine of x squared, so I want to know when is x squared equal to pi. Ooh, that's not pretty, going to move it down here. That means that x is equal to the square root of pi. And it's the positive root because we're to the right of the y-axis. So my upper limit is going to be at radical pi. Now that seems rather awful because I don't like having limits like that in an integral, but it turns out to be pretty nice. When I step back and look at this integral, I see that x squared's derivative is 2x. And I love this because I have the 2 and I have the x. So when I do substitution, the 2x is right there. So u will be equal to x squared du is 2x dx. So when we make our substitution, we can also substitute for the limits of integration. If x equals 0, u equals 0 squared, which is also 0, and this is where things look prettier. If x is equal to radical pi, u is x squared, so it's the square root of pi squared, which is equal to pi. We'll make these substitutions and go ahead and evaluate the integral. So the 2 and the x became du. My integral is not from 0 to radical pi, but from 0 to pi. The 2 and the x stay there, and I forgot to put the pi out front, so we'll put it in the inside. And then u was equal to x squared. So this is going to be the sine of u, exactly. Sine of u. Much prettier than some of the integrals we've been dealing with. The antiderivative of the sine of u is negative cosine of u. We want to evaluate that from u equals 0 to u equals pi, and we'll go ahead and do that. And we end up with an answer of pi after we do all of our substituting. In this example, we're going to see how we might have to adjust just a little bit what we mean by the height of a particular shell. We've got the curve y equals 4 minus x squared and the line y equals 3x in the first quadrant. The y-axis also acts as a boundary. We want to find the volume of the solid generated by revolving that region about the y-axis. Here are the graphs of the two curves in question. The region we're discussing here, we've got y equals 4 minus x squared right there, y equals 3x, and the x-axis, and the y-axis. You got to be really careful. It's really helpful if you use colors. That region is what we're going to revolve about the y-axis. So it's this region in here. Now it is possible to do this one with the disc or washer method. I advise against that because if you look at a region in here, notice that the rightmost function is the line y equals 3x. And when we reach y equals 3, then the rightmost function becomes y equals 4 minus x squared. If you want to revolve it about the y-axis using the disc or washer method, you would need to integrate with respect to y, and each of these would need to be solved for x. Solving y equals 3x for x is not difficult, neither is the other, but it gets kind of messy because you have to introduce a square root. So I prefer to go ahead with the cylindrical shell method. Once again, another thing that leads me to believe that I want to do that is the function is given to me in terms of x's, and I'm revolving about the y-axis. When the functions are in terms of x and you're revolving about the y-axis, your choice is only the cylindrical shell method. So let's go ahead and draw a typical rectangle. There we go. Let's draw its mirror image on the other side of the y-axis. Not quite the mirror image, I'm a little too close there. And that would be my typical shell. The thickness, again, I like to think about it as drawing this little rectangle, finding the area of that rectangle. That width there is dx. Ooh, the height of this rectangle is going to be a little bit more challenging. Not too much more. Where are we moving? We're moving up and down. On the top, the ordered pair there is x comma 4 minus x squared. On the bottom, we have x comma 3x. And so the distance between those two would be 4 minus x squared minus 3x, or simply 4 minus x squared minus 3x. So that is the height of my typical shell. And then the last thing that we need to do once again is find the distance around the shell, which is again the circumference. And the circumference here, we need the radius. The radius is measured from the y-axis, the axis of revolution, out to the point. We went from 0 up to x, so my radius in this case is equal to x. Now we put this all together. The volume is 2 pi times my radius. I'm going to stick the integral sign in front of that. My radius is x. Multiplied by the height of the typical shell. Our height, remember, was 4 minus x squared minus 3x, multiplied by the last dimension of that big box, which is dx. Now what we have left out of this is the boundaries of my particular region. We start at x equals 0, we end at x equals 1, so we're going to go from 0 to 1. Now, in order to evaluate this integral, we will need to distribute the x through. So we get 4x minus x cubed minus 3x squared dx. And then we evaluate the integral. In our next example, we're going to revolve about a line that is parallel to one of our coordinate axes, but isn't one of them. So we want the volume of the solid, we've got x equals y squared. That's a little hint about how we might go ahead and do this. The region bounded by x equals y squared, x equals 2 minus y squared. We're going to revolve this about the line y equals 1. X equals y squared is like y equals x squared, but laid down on its side. And then x equals 2 minus y squared will also be a parabola. The largest that value can get would be when y is equal to 0. When y is 0, we'll have x equals 2. In other words, we're going to plot the point 2 comma 0. And then when y is equal to either plus or minus 1, we'll have 2 minus 1 or essentially 2 minus 1, which is 1. So when y is plus or minus 1, we will have x equals 1 as well. So the region we're talking about, we said it's the region bounded by these two curves. It's this region in here. This is going to be revolved about an unusual line. It's going to be revolved about the line y equals 1. So this is a rather challenging problem, actually. All right, because my functions are given to me in terms of y, x equals y squared, I think I'm going to want to draw rectangles that are thin in the y direction. So here is a rectangle that spans that region where it's thin in the y direction. Because it's thin in the y direction, we're going to think of this as a dy. I'm revolving it about the line y equals positive 1. Now look where we are. We are this distance from the axis, so we need to take the same distance from that axis on the other side and draw the mirror image rectangle. And then we can draw the typical shell, which connects these two. Our shells this time are kind of laying on their side as compared to the ones we were dealing with before. Okay. So that's what it's going to look like. We know one of the dimensions of that rectangle, or the rectangular prism, if you will, the box that we pull out, one of the dimensions is going to be equal to dy. Okay? Another dimension is going to be the length of this particular shell, which is, okay, now again, we're moving from left to right. Where do we start? We start at x equals, well, let's see here. The one on the left is y squared, and we end at 2 minus y squared, right? Because the left one is on this curve, which is x equals y squared. The rightmost one is on that curve, which is 2 minus y squared. So this total span, this total distance across, is going to be the rightmost value. The larger value is always on the right, 2 minus y squared minus y squared, which is equal to 2 minus 2y squared. That will be our second dimension that we need to deal with. And finally, okay, now comes the challenging part. Now we need to do the radius. Remember, the radius is the distance from the axis of revolution to the point on the curve. Now, I haven't labeled my points. Let's label the points. This is the point x, comma, y. The radius is the distance from the axis, y equals 1, to that particular value. Now, in which direction am I moving? I'm moving up and down. Where did I start? I started up here at the point 1. Okay, I started at 1, and because I'm moving up and down, I'm looking at the differences in y values. The ordered pair, x comma y, has a y value of 1. So the distance between these two is going to be 1, the top value, the value that's above the other, 1 minus y. If I'm moving up and down, the value that's larger will always be on top. The top value, 1, minus the bottom value, y. And so now we have the luxury, the joy of putting all of this together. Remember, that's my radius that I just drew there. So that's the radius is equal to that. Here we go. The volume is 2 pi. Again, I forgot to deal with the limits of integration. We can always do that later. 2 pi times 1 minus y. That's my radius, multiplied by the height of the cylinder. Well, the height of the cylinder we found over here to be 2 minus 2y squared. And then multiplied by the thickness, which we found to be dy. Lovely. Now, what have we not done? We have not dealt with the limits of integration. We are integrating with respect to y. We're integrating with respect to y. Because of that, I need to think about the range of y values that I encounter in this region. So, down here at the bottom, this bottom point is the point 1 comma negative 1. The y value is negative 1. Up here at the very top of the region, we have the point 1 comma positive 1. So y varies between negative 1 and positive 1. Those will be our limits of integration. Okay, now in order to evaluate this integral, we're going to need to expand it out. I actually notice that we have a common factor of 2 in that second factor. So I'm going to factor that out, multiply it by the 2 that's out front here, and we'll end up with 4 pi times the integral from negative 1 to 1 of 1 minus y times 1 minus y squared dy. That's just, I mean, you didn't have to do that, but I think it makes our calculations a little bit easier. So I'm going to expand this out, find the antiderivative, substitute things in, and go through the calculations in one quick step here. If you need to, pause the video for a moment to see how I got to where I am, but I found the antiderivative and I substituted both +1 and -1 in. I'm also using the fact that +1 to any power is going to equal 1. -1 to an even power is +1. -1 to an odd power is -1. I've utilized those things. And so when we expand all this out, we end up with 4 pi times this minus 4 pi times all of this. If we distribute, collect things, and so forth, we end up with a final answer of 8 pi over 3. And now for kind of a quick recap of the two methods that we know for volumes volumes of solids generated. The disk method, we end up with something that's very similar to pi r squared h, essentially. So that's the volume of a cylinder. Now that's the basic formula. I used t's here instead of x's or y's, depending on whether or not we're revolving about the x-axis or the y-axis. For the shell method, we have something similar in terms of circles. We have the circumference 2 pi times some radius. Again, that may not just be x or y. We might have to do some extra calculations for that. But 2 pi times the radius multiplied by the height of the shell and multiplied by the thickness. Okay. Here are some problem-solving strategies that I think are very helpful. If you are given a function that's in terms of x, and you want to revolve it about the x-axis. So we're going about the x-axis or a line parallel to it. And it's in terms of x, you're probably dealing with the disk method problem. If you're not, then you would need to switch it so that your function is in terms of y. On the other hand, if you are in terms of x and you're asked to revolve about the y-axis or a line parallel to it, then we are dealing with the shell method. Again, these are just kinds of hints as to what method you might want to use. They're not set in stone, so you might need to convert it to the other variable. Graph them, and then graph them again. As I mentioned, they're often solved for x or y. Use the variable to help give you an idea of where you might want to try first. Do I want to try shell method first, or do I want to try the disk or washer method first? When integrating with respect to x, draw thin vertical rectangles. When integrating with respect to y, draw thin horizontal rectangles. Draw several of these disks, washers, or shells to get a good picture of what's going on. And after you set up, determine if you can do the antiderivative. There aren't too many problems, but every once in a while you'll encounter a problem where you set the problem up perfectly correctly, and then you can't find the antiderivative very easily. You have to go to the other method. So for our final example, we're just going to set up two integrals, one using the disk method and the other using the shell method, just to illustrate exactly what's going on. So we want the coordinate axes, y equals radical 4 minus x. We're going to be going about the x-axis. Here is the region that we're revolving about the x-axis. We first want to do, let's go ahead and since we have it in terms of x, I'm going to draw a rectangle that is thin in the x direction, which means I would be using dx's. When I do this, here is the rectangle. Here is the mirror image of that rectangle. When I revolve it, it would generate for me a disk as opposed to a shell. When you're integrating with respect to x, going about the same axis, the x-axis, it's going to be a shell method problem or a disk method problem. We need to know two things. We need to know the thickness. Our thickness is dx, and we need to know the radius. Our radius is the square root of 4 minus x. We set up the integral. The volume is pi times my radius squared times h. Now, because I'm integrating with respect to x, dx again, we observe that our lower limit is going to be 0 and our upper limit is going to be 4. So our final answer, I don't have to evaluate this, I just have to set it up, is pi times the integral from 0 to 4 of the square root of 4 minus x, that's my radius, squared times the thickness, dx. So if you want to, that's pi times the integral from 0 to 4 of the square root of, no longer square roots, right? That's the bonus. Just 4 minus x dx. Now let's do the shell method instead. If I do the shell method, I'm going to have to take this and I'm going to do this in green. I'm going to have to take a shell that looks something like this. Okay. I'm going about the x-axis. I need to have my shell thickness in terms of y. So this is a dy. If I look at the mirror image of that, there is the mirror image. We draw the shell. This is getting really crazy with the shells and the discs in the same picture. But that's kind of what it looks like. Now we know one dimension of the box that we make by cutting this open and laying it out. One of the dimensions is dy. The other dimension is this height of the shell. Again, notice we're moving left and right. The height of the shell is the x value. Oh, wait a minute. But if I'm integrating with respect to y, this has to be solved in terms of y. So if we square both sides, we get y squared equals 4 minus x. If we add x and subtract y squared from both sides, we end up with x equals 4 minus y squared. So this distance is x equals 4 minus y squared. We need the height of the shell. We also need the radius of the shell. And the radius of the shell is the distance from the axis of revolution, which is x equals 0, up to, or y equals 0, up to the y value of that coordinate. So the radius in this particular case is simply y. And we'll put this all together. So the volume was 2 pi times my radius times the height of the shell multiplied by the thickness. In our case, and once again, I haven't dealt with my limits, we'll get to that. My radius is y. The height is 4 minus y squared, and the thickness is dy. What about the limits of integration? Well, the limits of integration come from the possible y values we can encounter in this region. We're starting at y equals 0, and we're making our way up to y equals, well, the maximum y value is there at that point, y equals 2. So we're going from 0 to 2. If you want to integrate this, you would probably want to distribute the y through there to get 4y minus y cubed dy. If you evaluate both of these integrals, the first one we got from the disk method, the second one that we got from the shell method, you will end up with the same answer. It's kind of interesting that you would get that. And I believe the answer is 8 pi, but I'm making a guess at this. And I'm using this to make that guess. See if you can figure out what I did without doing any integration.